nitration. Nitration is one of the unit processes. We've defined what a unit process is. We've talked about the reactors. So the unit processes we can see here. So we'll start with nitration. Nitration is just the introduction of one or more nitro groups. So the introduction of nitro groups to a molecule, okay, or a reacting molecule using various nitrating agents. Usually nitrating agents that are being used is a mixture of concentrated nitric acid and sulfuric acid. So a mixture of these two serve as our nitrating agents. So, and then this can actually be done in batch or in a continuous process. I mean the introduction. So nitration is employed in chemical activities. It's employed in chemical industry as in the making of dye stuff, pharmaceuticals, and so much more. They serve as making of explosives such as TNT, that's 3-nitritoluene. Okay, this is an explosive and it's used in the making of nitrobenzene. So it's also used in the making of nitroparaffins, that's alkanes with nitro groups. So now this is just a little bit about nitration. So we'll be looking at how nitration is involved in the making of nitrobenzene as an example. So nitrobenzene is one product of nitration. We'll be looking at the reaction mechanism of the production of nitrobenzene via nitration. Now, the key reagent in the nitrification or the nitration of benzene is nitric acid. This is nitric acid. Okay. Now, this nitric acid is an electrophile. It's a very slow acting electrophile. Electrophile are electron deficient chemical species and they're electron acceptors. So it's a very weak, a slow acting electrophile. Okay. And in the presence of benzene, remember we want to nitrate benzene, production of benzene. In the presence of benzene, which is a weak nucleophile, benzene is a weak nucleophile. It has a lot of electrons around it, but it's a weak nucleophile in the sense that there are no activating groups. You can compare benzene with, let's say, toluene, right? You can compare this because it has this group, and we can compare toluene to phenol. All right, so there's the presence of very strong activating groups here, and this group can actually direct incoming chemical species to the auto and para. You see, it's an auto para director. So, but we will not be looking at this. So I'm essentially telling you that benzene is a weak nucleophile, while nitric acid is a slow acting electrophile. So in the first stage, in the presence of sulfuric acid, if you remember, the nitration process involves the use of concentrated mixture of nitric acid and sulfuric acid. All right, so now what's the first stage in the nitration of benzene? Now we're going to have the sulfuric acid. This is the sulfuric acid. Let's have the molecular structure of sulfuric acid. All right, H2SO4. So this is how it's bonded. Now we can provide the electron dot structures. Oxygen is 6 valency, so we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. So this is sulfuric acid. Okay, and now how about nitric acid? Because the nitric acid has to be activated. We need to produce a nitrosonium ion that will bond to the benzene. Okay, so essentially we need to produce it, and then the chemical formula for nitric acid: nitrogen bonded to oxygen. Then how many oxygen? 3 oxygen, so we can have OH, right? Then we can have one more oxygen here, so we can have an oxygen here. All right, so if you noticed, nitrogen valency of nitrogen is 5, That is why we are having 1, 2, 3, 4. So it has used 4. 1 is left, so it is deficient of 1 bonding. So we can have it positive here, as you can see. And then oxygen, look at oxygen, should be 6. 1, 2, 3, 4, 5.
Basically, the positive charge on the nitrogen is due to oxygen being more electronegative, so it withdraws the whole electron to itself, having excess charges, so partially negative, and nitrogen is partially positive.
So in that regard, we now have, let's look at the dot structures. Oxygen 6, right? 1, 2, 3, 4, 5, 6. This is very important. 1, 2, 3, 4, 5, 6. All right. Now that we've satisfied all conditions, now if you look at the sulfuric acid, this is an acid, right? So it's going to generate a proton, but then this oxygen hydrogen bond, there's going to be an electron drift to the oxygen. Oxygen is going to pull the whole electron being electronegative to create a partial positive hydrogen here. Now this is oxygen hydrogen bond here too. Now what is going to happen is that the oxygen is going to donate, pick up this proton. Okay, can you see that? So once it picks it up, there's going to be a partial positive charge here. Now let me draw it just for a little clarity. Once this reaction happens, first off, here is cut out. So we're going to have a net negative charge here for oxygen. So we're going to have this sulfur. Once hydrogen has been abstracted, okay, so this is here, and then oxygen is going to pick up the proton. All right, so the whole of this is going to attach to the proton, so we have nitrogen, remember we have a positive charge here, right? Net positive charge here. So we then have those two electrons is forming a bond with hydrogen. So we have oxygen, these two electrons is forming a bond with hydrogen, right? Each two electron, a pair is a bond. So we have a bond to hydrogen. Let's draw that, a bond to hydrogen. Remember, we still have non-bonding electrons here, so we have 1, 2. All right. So, but once this is done, if you look at the valency of oxygen here, it's 1, 2, 3, 4, 5. So it is deficient of 1. So there is a net positive charge here. So can you see? And now there's just going to be some balances. Now, if you look at this, this is essentially water. This is H2O. So what is going to happen is that oxygen, being more electronegative than nitrogen, is going to pull this whole bond to itself like this. So once it does this, okay, once it does this, there's going to be a net positive charge here too again. But then there is some electron here. To balance this charge that is here, the oxygen is going to donate this electron to the bond. So we're going to have something like this. Okay, so essentially what we'll be producing from this reaction is nitrogen oxygen bond, as you can see here, with a double bond here. You see it's donating an electron, so we can have a double bond to the oxygen. All right, so we have these pairs, 1, 2, 1, 2. All right, so remember there was an electron drift to oxygen, so there is a net positive charge here still evident. So we're going to have this. All right, and this has detached itself. All right, so we're going to have plus water plus H2O. So you can see this. So essentially what we want to produce to nitrate the benzene is the nitrosonium ion, as you can see here. The nitrosonium ion is going to undergo what we call an electrophilic aromatic substitution, because this is an electrophile. Okay, it is electron deficient, as you can see, then but it is a weak electrophile. All right. And then, so now the next step is the nitration of benzene itself. So this is what we've produced. This is what will now carry on with the process of nitrating benzene, the nitrosonium ion. So now let me wipe this off. So remember we've produced our nitrosonium ion, okay, with a partial positive charge. All right. This is our nitrosonium ion, and where is our base, our benzene. So we have a benzene ring. Okay, I'm gonna draw it to show the hydrogen atoms. So we have this. Essentially, we want to nitrate benzene to show the nitration process in order to produce a nitrobenzene. So now look at it. Look closely. The benzene itself is a weak nucleophile, and it has a lot of electrons it can actually donate. So now what is going to happen is that there's going to be a bond formation. So the pi bond, one of the pi bonds here, is going to pick up the just going to donate electron pair to the nitrogen to form a bond. Okay, so once this is done, as you can see, this bond, this pi bond, the pi bond consists of 2 electrons. Okay, you're going to form a bond to nitrogen. All right, and when it does, we're going to have this. Let me draw this again. Just look closely. We have these ones. They will have hydrogen. We have hydrogen. We have hydrogen. We have hydrogen. But look closely. Once this is done, that means the carbon here is left. If you look at it here, this is 1, 2, 3, 4. Carbon here is surrounded by 4. But in this case, once this is gone, carbon here will be surrounded by 3 because 1 electron is left here. So here there's going to be a net positive charge. Now the bond itself will form, we're going to have, remember this and hydrogen. So this bond is going to attach to the nitrogen. So we're going to have this bond attached to nitrogen, and you know the nitrogen has the oxygen, double bond oxygen. All right, and there's something that's going to happen here. I'm going to show you now. Okay, there's something that's going to happen here because nitrogen itself is having a positive charge. So what is going to happen is this is 1, 2, 3, 4, 5. So what is going to happen is oxygen is going to withdraw electrons from the nitrogen. Okay, we know that oxygen is more electronegative than nitrogen. So we're going to draw this electron just to balance the electron. So it's going to take up the pi bond here to itself. So we're going to have something like this. So the whole of this bond is going to come to oxygen just to balance the whole process. So we're going to have a nitrogen oxygen single bond here with this. This is happening due to the fact that there's an additional. So if you look at it now, let me make this a little bit clear. If you look at this closely, you can now see that we've formed a bond between the carbon to the nitrogen. The carbon here is satisfied, 1, 2, 3, 4. Now look at it again. We have a nitrogen surrounded by how many electrons? 1, 2, 3, 4, right? It is deficient of 1. So in as much as it is deficient of 1, so we have a positive charge here. Now stability is going to happen. There's some degree of stability. Aromaticity has to be restored. So what will happen to this positive charge? The positive charge, the hydrogen here can actually donate the electrons back. So it's going to be some electron drift back to the bond. So once this is done, this hydrogen, a proton, is generated. You can see, all right? This proton that is generated can now add up with you. If you remember, we produced from the sulfuric acid, we produced the sulfur ion. So we had something like this, right? With sulfur, oxygen, we had this in the previous steps, if you remember. So the proton that is generated is going to be picked up by this ion here from the sulfuric acid, so the proton have this. So once it picks it up, definitely a bond will be formed. So we're going to have, this is H2SO4 will be formed as one of the products. And remember, the aromaticity is being maintained, is being generated. So we're going to have this as our final product, which is benzene. The benzene ring, remember, there's going to be a double bond here just to balance the whole process. So we're going to have hydrogen, we're going to have hydrogen, hydrogen, hydrogen. Then we'll have nitrogen here with double bond oxygen, all right, with a partial positive charge, right? So with single oxygen, nitrogen to oxygen bond, with a partial negative charge. So this is nitrobenzene. So this is our product. So this is going to be our product, and this is how you essentially produce nitrobenzene via the process of nitration. So this is basically it, and that is how you produce nitrobenzene.